Chapter 1, Lesson 2 of Precalculus. We're looking at the characteristics of functions when analyzing, and in this video we are going to look at domain. Domain, you remember, are the x values that you can substitute into the function, and graphically speaking we're talking about all the numbers along the x-axis. So these are all real numbers that we can use in the function that we are looking at. Restrictions can occur when you try to use an x value that creates something that's mathematically undefined, such as a 0 in the denominator or a negative number in the radicand. And we're going to talk about each one of these separately, and there are three scenarios that are going to create these restrictions. As I've already said, you can't have a 0 in the denominator because that is undefined. You can also not have a negative radicand because that also is undefined with real numbers, and undefined with real numbers. Negative square roots can be dealt with using imaginary, but we're only talking about real numbers, the numbers on the x-axis. And the third scenario where you will have restrictions in the domain is when you're actually applying the function to a real-world situation. So we're going to look at these three separately, and the first two we're going to look at them algebraically how to figure it out. Then we'll look at graphically how to figure those out, and then we'll look at the last one, the application. So the first scenario is a 0 in the denominator, which you cannot have. So if you're asked to determine the domain, you need to set the denominator not equal to 0 and then solve for x. So for this instance here, we have 2 divided by x minus 3. We know that the denominator here cannot be 0, so we set up this equation, or not equation, depending on how you want to look at it, and then we solve it as we would in any other equation, and we solve it and we get the domain restriction that x cannot be 3. Now, to give the domain, we want to use interval notation. So how does x does not equal 3 look like in interval, or what does it look like in interval notation? And you imagine a number line in interval notation. So if we can't use 3, we can start all the way down. What I like to do is imagine a number line, and I start down in negative infinity, and starting in negative infinity I can go all the way up to 3, but I can't use 3. So that takes care of the numbers to the left of 3. And then I need to include, so we're going to use the set symbol. If you haven't seen this before, this is just a U. It means in union with, meaning both of these are included. So not only do I have the numbers that are less than 3, I also have the numbers that are 3 and up greater than 3 as well. So this would be the interval notation that describes the domain of this particular function. Okay, so we're going to use interval notation to do that, and that's what that would look like. So this would be my interval notation. Now, the second type of mathematical restriction we have to be careful of are negative radicands. And again, we know that our radicand must be greater than or equal to 0. So as long as it's 0 or greater, that's okay. So we set the radicand greater than or equal to 0, and then solve for x. So in this case we have x plus 3 is greater than 0, or the radicand here is x plus 3, so I need x plus 3 to be greater than or equal to 0. And then that's going to solve that inequality. I'm going to get x greater than or equal to negative 3. So then we have negative 3 up to infinity. This would be the domain. These are the x values that I can use. I can use any number that's greater than or equal to 3. Okay? Now, there is one thing that happens when you're talking about radicals, and that's what happens when you have squares underneath the radicands. And we're going to treat that as an absolute value. In other words, if you ever have a plus or minus when you go to solve for the radicand restrictions, you want to think about it in terms of absolute value. And I'll show you what I mean. If we have the square root of x squared minus 4, we know that this radicand must be greater than or equal to 0, so we set that up to greater than or equal to 0. We then solve that inequality, and we get x squared is greater than or equal to 4, and because I take the square root in this step right here, you'll notice that I end up with plus or minus 2. Now what does this mean? This means my domain are all x values that are more than or greater than or equal to positive 2 and negative 2. But the negative 2 creates kind of a weird thing because it's talking about greater than 2, but it's talking about a value greater than 2. And this is why I say whenever you end up with a plus or minus here, you want to think of this in terms of an absolute value. In this particular expression, what does this mean? And as a review, if you remember from last year, when we have absolute values greater than or equal to 2, what that means is that the distance from 0 of x must be more than 2. And again, that creates two scenarios. If I go to the right, here's 2. The values bigger than 2 are these up here. So that is part of my domain, because again, I'm thinking about this in absolute values. So I can use numbers that are greater than or equal to 2. So that creates that. But again, I'm thinking about this negative 2. If I think about this in terms of absolute value, if I go to the left 2 units, this is 2, the numbers that are more than 2 away from 0 are these over here. All of these numbers are more than 2 away from 0. Okay, so these numbers are also in my domain. So these numbers begin in negative infinity, again, thinking about going from left to right, all the way up to and including negative 2. So these would be, or this together, or in union, would be my domain. So when you have a square that's in your radicand, when you get this plus or minus, you want to think of this in terms of greater than or equal to. So that's how you determine domains when you're doing them algebraically. Okay? Graphically, what a domain is when you look at the function and its graph, you can imagine a vertical line moving along the x-axis. And if that vertical line crosses the graph, then that x value is in the domain. If you have a case where the x value, as you move the vertical line along the x value and it does not touch the graph, then that x value is not in the domain. Okay, so imagine a vertical line. If the vertical line crosses the graph, then that x value is in the domain. If the vertical line does not cross the graph, then that x value is not in the domain. Let me show you a quick example. If we take a look at this function here, we have this function here, this graph, and it goes up here. Now, if I take this vertical line here and I put it right here along the x-axis, and let's say this is at x equals negative 3, you'll notice that this vertical line does not touch the graph of the function that's over there. Therefore, this number, this x value right here, is not in the domain. So all of these numbers over here, wherever the vertical line does not touch the graph, those x values are not in the domain. Now, as soon as I reach here, as I begin here, and let's say this is at 3, okay, need a black on black doesn't work. Okay, that means that starting at 3, this line touches the function, or it crosses the function, and as I go up here, that vertical line continues to cross the function. So that means my domain starts here where this vertical line crosses that function. So it starts at 3, and whoops, 3 is included, and then it goes up to positive infinity. So graphically speaking, you can kind of think of it this way. Think about a vertical line. If it crosses the function, that particular x value is in the domain. If it does not cross the function, then those x values are not in the domain. So that's what it looks like graphically. The last scenario then is the application model, what's going to create restrictions. And what that means is you need to use the domain that fits the situation when you're applying this to the real world type of problem. The algebraic domain allows for all x values along the entire real number line there, so anything. However, some of those lines or some of those values would not be practical for the situation at hand. So for example, excuse me, just finished lunch. For example, if we're talking about volume, the volume of a sphere is 4/3 pi r cubed. Now, if I just look at this function algebraically, there are no variables in the denominator, so there are no restrictions because of that. And there is no radical in the equation, so there is no restriction for that. So the algebraic domain for this particular function is all real numbers. However, because we're talking about volume, and this value here, r cubed, is talking about the radius of a sphere, negative numbers for radius doesn't make sense because a sphere can't have a negative radius. All the numbers are positive. So while the algebraic domain would be all real numbers, because we're applying it to volume, numbers that are negative doesn't make sense. So our domain has a restriction based upon the fact that we're applying it to a real world situation. So we would only use numbers that are 0 or greater. Now 0 maybe doesn't even make sense either because a sphere with 0 radius wouldn't be anything. So 0 might not even, a better answer here might be 0 is not included. So those are the three types of examples where you will get restrictions.